Yo, what up? It's late. Your boy had too much soda, and we're wired. So here we are. I went over to Dollar Tree and we got a liter and a half of Dr. Pepper. Had about half that thing. Now now here we are. Yo, what's up? All right. I was like, let's just stream. Why not? All right. What's good, everybody? Hope you're having a good day. Good night. I think we're probably gonna get a lot of the India crowd in tonight because I'm streaming late. It's probably day for them, which will be good because they like C. They'll like this kind of stuff. All right, let's go. Let's get right into it. All right, we're back in C programming, a modern approach. We're gonna be taking a jump at these programming projects. I went ahead and just ran this simple. I learned that you can do for loops in the terminal here, so I've been doing this more. It's pretty fun. You can do these little for loops to just create files and directories really fast. So I kind of want to see if I can recreate this. Let's see if I can delete these. Let me see if I can go. Let's try this again. So let's bring this back. So we're going to see make dir, and then can we? I don't know how to do it. I'm gonna look up at whatever. How to make dir and file for loop in okay, yeah, so we'll do this. And then we'll say touch chapter 4 programming project. Ooh, hold on, can I go back? Let's try that again. I want to go .c. It didn't work quite as what I thought, but whatever. We got the files, so we'll just throw them in here to the respective folders. Not quite what we wanted. I thought it would touch inside of those folders, but I guess not. And it didn't make them all? Oh, it just did it to 6. It didn't do it to 5. Oh, here's 5. Oh, it just made them and dumped them all in the last one. Yo, Mike getting tonight on nights. Hold on, we gotta find that. Mike at night, Nick at night. Yeah, that's a funny thing. I should make it Mike at night. That's a good one. Usually I just do after hours. But I was telling my intro when I first came on. What's up, Jimmy? Welcome back in tonight. I appreciate you coming. Yo, what's up, Ray? Welcome back, dude. I was saying I walked over to the Dollar Tree next door and I got myself a liter and a half of Dr. Pepper, and next thing you know, here we are. We're juiced. We are juiced. Let's go. So we're just gonna bang out these programming projects tonight and have a little late night stream and show. But Let's look up Tonight on Nights. Yeah.
Tonight on Nights.
Now here's a good show.
There we go.
Tonight on Nights.
Now here's a good show.
We got a white Bronco heading east into the forest, requesting backup.
It's time for the men in steel to teach these madcap mammals their devil-may mare attitudes just won't fly.
Police brutality!
With the knee, no, that's so risky. Pepper spray,
Get
no.
away with it, or did someone let the cat out of the bag?
Capitalist, be done.
Catnip. That's not mine.
That's no mine.
Hold on, I'm the princess
One
Fiona.
of the greatest animated series
Shrek, I'm
ever.
her husband. Shrek, ow!
Nice.
Quick, rewind it.
Shrek, I'm her husband. Shrek,
Oh, I
ow!
love it. We gotta watch this movie. I gotta watch that movie again. Tonight on Nights. Getting turned on the old Dr. P. You know it. You know it. Alright, here we go. Let's go ahead and do these programming projects. Alright, let's get into this, yo. Okay, here we go. Write a program that asks the user to enter. Again, we're back in C Programming Modern Approach, 2nd edition, chapter 4. This is the end of chapter programming project. We completed the exercises earlier this evening. So, appreciate you guys for being here. It's 12:30 a.m. for me right now. We're gonna be grinding. Okay, write a program that asks the user to enter a 2-digit number, then prints the number with the digits reversed. A session with the program should have the following appearance. Read the digit using the %d conversion specifier, then break it into 2 digits. Hint, if n is an integer, then n modulo 10 is the last digit in n, and n divided by 10 is n with the last digit removed. Okay. Okay, so this one's not too hard. It just wants us to use this kind of trick though. So we'll include the standard io.h header file. And we're going to int main void. And then let's go ahead and do this. So this is pretty simple. So we're going to call printf. And we're going to say enter a 2-digit number. It's very clear you watch a lot of Shrek as a child. Yeah, dude, I did. My family, we had one of those like Suburbans, you know, white people cars. We had one of those white people cars, and it had one of those TVs in the ceiling. You punk, and it comes down. It was like really small. It was like that big. It was like really small. But like we would watch. I remember like we would just get fixated on a few movies and watch those growing up. And like that one, my brother got fixated on like Polar Express. So we'll do a scanf. The reversal is, and then we'll take in a scanf here, and we need to. Oh no, sorry, that's a printf. The scanf is going to be just a %d, and we're going to take in num, and we're going to save this in memory. And let's go ahead and create and declare a int num in our script here. And then let's go ahead and keep rocking. So what else do we want to do? Baby Mike locked in. Yeah, we were locked in. I didn't get one of those cars until like my brother came around though. So growing up as a child, there was a lot of like just on the VHS on the like the small like old like VCR TVs or whatever, you know, and CVR or whatever. I can't remember, CRT TVs. Back in the early 2000s. Those were the days, the good old days, man. Those are like, I remember that. It was so fun. Playing like GameCube on that and stuff. Okay, so now we have the num saved here. So we need to get the last digit. So we're going to if n is an integer, then n modulo 10 is the last digit in n. And n divided by 10 is the last digit removed. Right? Oh, so it wants a 2-digit number specifically though. Cool. So we can just put these rules in. So let's just call printf. And what we'll say is we'll insert in the reversal is, and then we'll put in %d here, and then %d. And then what we'll do is we will do these. So the n modulo 10 is the last digit in n, right? So we would want that to be the first digit. So this is going to be num modulo 10. And then the next digit that we're going to insert in here to this integer specifier is n floored by 10. Right. So yeah, 28 divided by 10 is like 2 point something. So if we floor it down to 2. Nice. So, and then we'll just return 0 here. So let's go ahead and open up a terminal here. Let's go up to our compiles here. This is going to be number 1, programming projects. Project, and then same thing for this guy. Right, and then we'll run this. Oh, whoops. Ellipses. There we go. Look at us compiling out here. So we'll compile, we'll run this and do, this is going to be number 1. Oh, programming project. Eli. Oh. I had a typo in my thing before, rip. Okay. Oh, we got a little typo here, we need that. Boom! Okay, let's clean this up a little bit. Oh, I did it again. Keep doing it. Sorry, guys. Trolling you. Not 12. I gotta read this guy. There we go. 28, 82. Cool. Nice. Halo 2, Halo 3. I'm honestly Jimmy Bose. Don't hate me. I didn't really play Halo 3 at all. I did play Halo 2 a little bit at my friend's house, but My parents, I didn't get like an Xbox. I was more of like a Nintendo GameCube kind of guy, growing up, a little kid for a while. Played a lot of Zelda, a lot of Pokemon. Dude, so much Pokemon, Zelda, um, a lot of like smaller like indie games on the Game Boy DS. That was like I just tons of stuff on that, like a little bit more. But I didn't get like an Xbox until I turned like maybe like 11 or 12. And that's when I got Halo Reach, and so I'm a Halo Reach is probably my favorite game of all time. I got to go back and do a playthrough, but I need to get an Xbox when it comes out. I'm waiting for like a new console Xbox to come out. Maybe it'll be like cross compatible with a bunch of stuff. But I don't want to get like, I think there's gonna be a new console coming out soon, so I'm trying to wait for that one. Okay. If we get done with this quick, we might be able to play a game of League of Legends. If we're not too tired. Number 2. Alright. Extend the program from parametric 1 to 3 digits. Ooh. Okay. That's not hard. We just need to do this, right? So let's take our project from before. And then let's just do a 3-digit number. And then let's insert another %d here. And then we're going to do, I think we want to put num. So the middle number would stay where it is though, right? It prints it in reverse. Okay. So we would just need to do num divided by 100 to get the first digit. So num modulo 10 would give us the first digit. Num divided by 100 would give us, and then do we want, what does the W mean? Does it tell us what the W means? So maybe what we need to do is well, let me just do this. Let me just put like, let me just try this for now. CD chapter 4 programming project. Two. And let's compile this. What? Three digits, huh? Without slicing. I don't want to look over at chat. I don't want to give it away. I think we can figure this out. But you guys probably already know. Let's do like 3, 6, 7. 713. Okay, so we do get the 7. So now how can we get the middle digit? Now if we take 367 and divide by 10 to give you... Oh, I know how to do. So we need to get the first 2 digits and then take the modulo and get the last digit of that, I think. So we need to go num divided by 10 and then take the modulo of that, right? Something like this. 367. Oh, let's go! I'm freaking crazy. Let's go, dude. It's not even 10:30. Let's go. Yo, we just got that on the fly. I'm happy with that. To be honest, a lot of games they just don't put that hard in development anymore. Yeah, that game was so good. They had like a lot of like cool Easter eggs, and just the story was so good. And hey, how's it going, Oro? I remember I emailed Professor K and King once when I was in college. He even replied, "Nice, dude. Maybe we'll have to email him on stream." Hey, thanks for the sub saved. Or baved? Is it baved? I asked him if there was a Python book he's written, which he said he had not and has no plans. Oh, dang. I wonder like if we could ever like go like sneak into a lecture or something. That'd be a cool like thing we could do if we get enough like 10K special. His Java book is too fixated on the basic things. His C book is better. Java and Python really similar. Maybe he thought I did Java. Okay, cool. So that is number 2. Awesome, dude. I'm happy we got that one. That was a fun one. I'm happy with that one. Boom. Wait, hold up. One, 2, 4. Where's 3? What the heck? What happened to 3? What? Dude, my loop just didn't skip a number. I'm tripping. Okay, that's really weird. Did I move it somewhere on accident? These are the only things that are green in my... Okay. Ah. Okay, let's get back into this. Okay, number 3. Mike very happy with himself, high on Dr. Pepper. Yeah, we got that Dr. Pepper in us. That's why we're awake right now. Yo, thanks for all the subs, everybody. We've got a lot of subs tonight. Thanks, Jamal. Appreciate you so much for coming in. Yeah, I went to a Dollar Tree after our last stream, and I got some soda. I'm juiced right now, guys. Got the little kitty and my puppy laying in bed. They're like, go to bed. Okay, here we go. Let's cook. Let's keep cooking. Number 3, extend the program in programming project 1 to handle 3 digits. Oh, that was 2, sorry. Rewrite the program in Programming Project 2 so that it prints the reverse of a 3-digit number without using arithmetic to split the number into digits. See this program section. Rewrite the program from number 2. So let's rewrite the program from number 2 without using arithmetic to do the digits. Hint, see this. What, just enter the first digit, enter the second digit, enter the third digit? Okay, let's go look at that programming, that project that it has. Enter the first digit, enter the second digit, enter the third digit. Really? That's what it wants us to do? I thought I wanted to just treat this as a single integer. So it's not something to do with this check digit, I don't think. Because that's like specific to this UPC code. I think it just wants us to do it with 3 prompts. Right? But that feels kind of lame. Extend the program from 2 so that it prints the reversal of the 3-digit number without arithmetic to split the number into digits. Hint, see this. And that's how it does it. It asks for 3 prompts. But this is enter a 2-digit number that prints a number with a single decision. Using this, break it into 2 digits. Okay. Wait, I don't think so. That wouldn't make sense. Hint, see this. How could you say enter a 3-digit number? Okay, I'll just have the user scanf for 3 digits. I think because it wants like all those integers that was like defined maybe. Like say, right, first, second, third. And then we'll save these as first, second, and third, right? And then what we'll do is we'll put these as third, for second, first, okay, simple enough. Let's give it a go. Uh, 367. What did I do wrong? Oh, because technically it's looking for 3 digits. Right. And it's the scanf is taking that first anything I say as the digit. Shoot. Oh, so we just need to do this. We just need to say this has a field width of 1. I believe. Oh. A minimum field width of 1. No. That's a minimum field width, right? So like it. Oh, maybe I am trying. Okay. I think that's how we do this. This is a clever trick. Each reads %1d reads exactly 1 digit as an integer, even if they're entered like 1, 2, 3 together. Let's go. Okay. Nice. Number 3's done. Number 4. Oh, whoops. I want to go back. Okay, here you go. Let's cook, boys. How many people got in here? We got 18 people in here at 1 a.m. Y'all are crazy. Go to bed, you guys. You guys are hanging out with me programming? That's programming. That's so cool. Thank you guys so much for being here. Hey, Siloed, how's it going? Welcome back in. Welcome in. For those that are new here, my name is Michael. I'm awake right now because we chugged some Dr. Pepper earlier and we're wired, so here we are. My name is Michael. I'm a human biologist and a chemist. I have a degree in human biology and a minor in chemistry, and I have been teaching myself how to program for a little over a year now. We are pretty, have some good fluency in Python, intermediate level, I'd say. Able to kind of teach ourselves new libraries and stuff pretty quick. And now we're trying to dive into C and lower level languages to further expand computer science knowledge as a whole here. So welcome. This is C Programming, a Modern Approach by K.N. King, 2nd edition. It's a great book. He's a good professor from what I hear, and it's been a lot of fun working through these projects and getting some good practice. Yes, the stuff's kind of redundant, but I'm trying to get it to a point where I don't even have to think about doing these things, just like I did with Python. I'm trying to take that same approach by really grinding through kind of elementary level practice problems to where they become almost second nature. So when I'm attempting to do harder problems like on LeetCode or whatever, I can really focus on those problems rather than having to think about the syntax and all that jazz. I'm really trying to get seriously. So appreciate you guys being here and joining me. Welcome. Okay, let's keep going. Round 4, we're blazing through these. Write a program that reads an integer entered by the user and displays it in an octal base 8. So enter a number between 0 and this. In octal, your number is this. Oh, cool. This is not that hard. So we're going to go like this. I'll just take my boilerplate from before and return 0. So what we're going to do is we're going to do a printf call. And we're going to say enter a number between 0 and 32,767. Cool. And then we're going to say scanf, and we're going to scan in for an integer. And what we're going to do is we can just take this integer as is. I believe we don't need to format it here. And we will save it in num. And we'll save it up here. And then we'll go int num and declare that here. So then if I go ahead and say printf in octal, you guys know how to do it. Give it in chat now. I'm going to do it right now. I think I know how to do it, so I think you can spoil it. We're going to say %d. We're going to put in the num, right? Well, we're going to format this. How we're going to format it? Well, we're going to say that this is going to be a right bound number, so it's going to be positive. For its minimum field width, though, of 5 digits. Oh, what is this octal number? I didn't even read this part. My bad. I'm trolling. The output should be displayed using 5 digits, even if fewer digits are sufficient. To convert the number to octal, first divide it by 8. Okay, so there's a little bit of conversions we have to do. I didn't even read this part, you guys. Okay, hold on. So to convert the number to octal, first divide it by 8. The remainder is the last digit of the octal number, 1 in this case. Okay, we're going crazy. So last, I'll go here and say, we'll add in a last. Fifth. Is that how you spell fifth? I haven't spelled the word fifth in so long. Is it F-I-F-T-H? Yeah, I speak English. Fifth, fourth, third, second, first. Probably could have made those in the other order, but whatever. So let's go fifth is equal to, we want to take to convert the first divided by 8. The remainder is the last digit of the number, 1 in this case. So we're going to take our num and divide it by 8. But it says the remainder. To convert the number to octal, first divide it by 8. The remainder is the last digit of the octal number, 1 in this case. Okay, so let me see here. Where's my phone? Hey, what's going on, Engineer Baby? Yeah, we're gonna get into all that deep stuff. Going deep. How's it going, Shivam? You can watch some C++ conference for a good understanding. Oh, C++. Chill, bro. Chill. Keep up the good work. Hey, thanks so much for coming in. Defala. Appreciate you. I like that. Where am I from? The U.S. West Coast kind of guy. Okay. If you can't tell by the way I talk, probably. I've heard that people, when I went to college in like kind of more central United States, west central United States, people could tell. They're like, "Are you from the West Coast?" Like they could tell where I was from, like right away. Okay, so if we have 1953 and divide that by 8, right? Or is it? So that's 244. And then do we mod that by 8? Why does it say remainder? Which just 1. First divide it by 8. The remainder is the last digit of the octal number 1 in this case. Am I trolling? Like, why am I not getting this? Divided by 8. The remainder. $19.53 divided by 8 is $2.44. Floored. Right? The remainder what if I just 1953 mod 8? 1. Okay, so that's what it meant. Okay. So mod 8. Fifth is num mod 8. I wonder if I could actually just do, hold on, let me just do num here. Let me take in num, and let me put num maybe not. Because I have to, how could I just, okay, let's just do this. So if you do num mod, if you do this in fifth, then you call num, is there a mod equals? Well, you wouldn't want a mod equal. So this gets rid of the last digit. And then you divide it by 8. Right, so you'd have to divide 1953. And then if you do that, it gives you 4. And then take the mod of that, right? So then num becomes, then you do this. Then you keep going. Sorry, yeah, that just looks weird. I've never actually used that before. So you just keep going for fourth, third, second, and first. So 244 divided by 8 gives you 30. If you do 30 mod 8, well, let's think. We're not dumb. Right? So you can go into, you get 24, then you go to 32 from there. So you can go in, what, 4 times? With the remainder of, 24, 6. Hold on, what was the number? What was the math I was trying to do again? Completely lost that in my head here. Oh, 30. It's not 32. It's a remainder of 6, which is this guy. Then you do 6. No, 6 mod 8 would be trolling? I think I might. I don't know what this is asking. Printf is capable of displaying numbers in base 8 as well as we'll see in chapter 7. So there's actually an easier way to write this program. To convert a number to octal, first divide it by 8. The remainder is the last digits of the octal number. What does this mean? I don't know what this means. Am I like really dumb? For a decimal number base 8 to octal, you're rewriting the number using 0 to 7 digits instead of 0 to 9. The process works by repeatedly dividing by 8 and keeping track of the remainders. Yeah, I've had a problem like this on LeetCode. I remember sucking really bad at it. Each remainder comes one digit of the octal number starting from the last digit rightmost. Let's go step by step. Okay, hold on. No code. Each time you divide, there's a leftover part. That leftover. Then you just divide the result again. Okay, so each time you divide the leftover part. Oh, so it's remainder as in that leftover? Not as in mod. So 1953 divided by 8 gives me 244. And what do you do with that? The first remainder gets... No, so you definitely mod the number by 8 to get the last digit. Right? Then you divide the result again by 8 to get the next remainder, which becomes the next digit to the left, and so on until you can't divide anymore. So 1953 divided by 8 is 244. Did it just autofill that? I didn't write that. What the heck? This is remainder. This is the remainder. It goes in with the remainder of 1. The remainder 1 is the last digit of the octal number, the rightmost. Then you take the quotient and divide that by 8 again, because that's what we're doing pretty much here. So we figure out the last number, the remainder, and then we take the number and divide it by 8. And then we figure out this number and then divide by 8, this divide by 8, this divide by 8, this divide by 8. Okay, so I think we're doing it right here. So then we want to print this in the octal form. So, sorry. Oh yeah, so the first, second, third, fourth, fifth. That's how I set it up. Right? I'm on a whim here, you guys. I'm a little bit... It might be because it's late. I'm gonna blame it because it's late. So yeah, that's why. That's for sure why here. Oh, whoops. I don't want to go with this one. What am I doing? Project number 4. Oh. I haven't looked over at chat yet. I'm not trying to hit a spoiler. So if you chat at me, give me a second. Oh, I'm bad. I'm Python boy over here. Ooh, yeah, I'm Python boy for sure. Look at that. Oh gosh, trolling, man. Give me this guy. Okay, we want 1953. 03641. Let's go. Let's clean this up with a little \n, and we're good to go. Oh yes. Okay, I'm always really, I don't know what it is about me, dude. I can convert metric units like nothing because of chemistry and like the dimensional analysis that we did in college, and I do a lot of it at my job. But I don't know what it is about base conversions between like this stuff, octal and binary and stuff. It just really trips my brain, man. 03641. All right, let's go take a peek at chat. When you divide by 8, keep the remainder so you get the last digit. So if you divide by 8 and it has the remainder, call it 1. Doesn't have it, if it doesn't, it's 0. Then it counts from left to right. Which GCC compiler are you using? This is just the default one that came with my MacBook here. I'm pretty sure. I haven't added, installed, nothing. What's going on, y'all? Hey, what's going on, Simp? Jeez, crazy name. Hey, Eco Saviors, welcome. Zaid, when you get to pointers, you're going to need to learn how memory works. I recommend cs.app. You can read up to chapter 3 if it's dense, but worth it. Yeah, we've learned about pointers and a little bit of memory in our CS50X course. Definitely need to do a deeper dive for sure. It only had you, I think it like did a lot of the memory freeing for you. I think it only actually had you like free one thing of memory like in the whole that course. So definitely need some more practice with it, but I kind of get like the whole char star stuff. Definitely want to get a refresher though. It's been a while since we've talked about it here on the channel. We completed that course back in March 2025, so that all of that is live on the channel too. Okay, let's keep rocking here. Number 5. Okay, I like these tunes. Hey, how's it going, Rodolph? Hey, it's kind of, I like that. How long to master program? Dude, we got a long ways to go, my friend. Join along. Pull up a seat and let's get this going together, my friend. Imperial units are not real, though. Yeah, you're funny. We haven't gotten to like loop stuff yet, so I just repeatedly reduced the num down. Oh wait. So yeah, so I could reference it, but guess you wouldn't need this one, no? But whatever. But yeah, we haven't, I'm just going by what the book has given us. We haven't yet learned about looping yet. We know about it for sure, but we have, the book hasn't introduced us yet to stuff. But let me know if there was a different way. I'm all ears. Jimmy's got the jokes. I don't know, Zaid. So I work right now as a formulation chemist for a biotech company, and I do a lot of manufacturer controls, and I've been actually starting to build some software for, build some software for kind of computing like stuff pertaining to our like formulation. And it's not like anything, I don't really know if it's like professional software at all, because I really have no idea. I just wrote some like Python to Kinter GUI and like backend software. I mean software. I mean, God. Software. I mean software. Just like backend classes and object scripts, and with an overall like algorithm that kind of solves it. And yeah, I mean, it's whatever. I don't know. I would like to learn more though about what it like really is in a professional setting, because my work is fairly like analog and dated in their systems. So it's like version control is like, here is renaming the v2 to v3 of the Excel file. That's version control, and like, and then it's crazy. It's really disorganized. Okay, rewrite the upc.c program in section 4.1 so that users enter 11 digits at one time instead of entering 1 digit, then 5 digits, then another 5 digits. So it should be like this instead of, okay, so let's go ahead and go up to that 4.1 program and pull that down here. Move it right here. This is gonna take forever. I'm gonna try to copy it, but I don't think it's gonna work. It doesn't really like the copies. Yeah, I see. It's like it really has really bad formatting. I think we can fix it though. Let's do this. Let me do that. You can just delete this. Oh, gee. Okay, and so let's just see if we can fix this. Oh no, oh no. It's doomed. Oh my gosh, dude. Oh my gosh. Choking under the pressure here. And D, I1, I2, I3, I4, I5, J1, J2, J3, J4, J5. Okay, not bad. Then we have first sum, second sum total. Okay, and then we're going to do the following calls. Okay, enter the first single digit. Okay, so no, we don't want to do this. So now we're going to actually modify this part. So let's just get rid of this. Okay, here we go. That was a mess. It's late, guys. It's late. Breaking Bad. No, I wish. It's not that cool. I don't really work with like I rarely work with like drugs on the substance list and stuff. It's very like, I mean, sometimes I definitely have to like go through all that stuff, but not a big part of it. Okay, so we want to provide the user needs to enter it all at once. So, and then let's see what the format specifically it wanted, just so we're consistent. Enter the first 11 digits of a UPC. Printf. Enter the first 11 digits of a UPC. And then let's scan F here and take in this guy here. Oh God. I don't even think I needed to do this because we're taking it all at once. You gotta be kidding me. So we just need to do what we did before, but pull off the chunks at a time. Okay, that's kind of annoying. Sorry, you guys. I should probably maybe think a little bit ahead. So actually we're going to take in the number here. And then we're going to have to get the remainder here. Again, we haven't had access to loops yet. So we're going to have to do this just kind of robustly pretty much. So let's go ahead and say dude, I don't really want to. No, because we need to make these numbers. Okay, so what is the math that happens? It takes D, which D is the first single digit, so the first digit. It takes D, it adds it in this form, and then it takes the other ones, adds them, then makes a total, and then performs this mathematical expression to compute the check digit. Okay. So let's keep actually our things here, and let's have him take in the entire num, right? And then what we're gonna do is we are going to go so this is going to pull off the last digit. So the last digit in this case is the 8 here. Oh no, that's for that example. This one is this is the check digit. So 3 in this case. Yeah, here. Which 3 is our J5 value. For the first group of 5 and second group of 5. Okay, yeah. So J5 is equal to our num modulo we just want to get the first number off. So what do we have to do? Just 10. And then we have to take our num and divide it and equal it by 10 to reduce the number down. And then really quickly, I'm going to print f here to %d and stick in J5. And I'm going to call this and see if I'm on the right track here. Python, it's a little bit easier to just quickly check, I will say that. Oh, I'm trolling. So if we enter I guess it doesn't really matter like what we enter here. So we say 0, 1, 3, 8, 0, 0, 1, 5, 1, 7, 3. Okay, good. We're getting 3. So let's go ahead and call this down. J4, J3, J2, J1, I1, or 5, 4, 3, 2, 1, and D. So J4, 3, 2, 1, I5, I4, I4. Again, guys, we don't have like access to loops yet. We haven't learned it in the book yet, so we're just trying to be consistent with the expectations of the book. So if we've got to be kind of robust, then you know, it's whatever. Now we could probably just put these all together. We don't have to go line by line because it is C, right? It has that ability with these semicolons. Okay. So, hey Lance. How to riz women with the C programming language. It's funny. Hey Ali Forrest, how's it going? It's C Programming, a Modern Approach by K.N. King. Yeah, we played tonight. We had some Dr. Pepper, and we're feeling juice tonight still. So, thank you so much for coming in and hanging out with us. Yeah, let's go. Hey, thank you Alessandro and Jamal for the subs on YouTube. If you guys are watching and aren't sub, please do so. It's free. I really appreciate it. We up late right now. It's apparently one line that says, quote, you don't. Okay, that's the whole chapter. We got a funny guy. We got a comedian over here, Jimmy. Thought this was the first chapter. This is chapter 4, my boy. We're almost done with it. No, you can catch up on the other chapters, though. On my channel. There are a lot of great resources here. I think so. Okay, let's go ahead and compute now this code. So the math is right here. So first sum, it's going to be equal to D plus I2 plus I4 plus J1 plus J3 plus J5. And then we're going to have second sum going to equal to I1 plus I3 plus I5 plus J2 plus J4. And then we're going to compute a total which is equal to 3 times the first sum. Again, this math isn't really relevant to like C, it's just kind of for computing these UPC codes. Like, it's just like an algorithm in itself. Like, it's an example. Okay, so then we're going to print a check digit here. So the printf check digit, and we're going to insert the check digit here into our string, and we're going to put into our string this expression minus 1, and then we'll mod this by 10. Okay, so I think that'll let's try it. We'll find out. That's for sure. Okay, what's our code? You're not that guy, pal. Thank you so much for the follow, my bud. Hey, Faust. Faust, thank you so much. Appreciate you. You're awesome. 01380015173. Check digit is 7. No, check digit's 5. Oh, crap. D plus I2 plus I4 plus J1, J3, and J5. I1, I3, I5, J2, and J4. J5, 4, 3, 2, 1. I5, 4, 3, 2, 1. D. Bug on my end. User error. So what was our check? What was our code here? 01380015173. Check digit 5. Let's go. Let's go. Espresso. Espresso. I honestly, for a while, like, I'll be transparent. I honestly, for a while, I thought that's what it was. Like, growing up. I honestly was like, yeah, what? I was one of those people growing up. I also, like, growing up for some reason, like, I don't know why, like, I didn't really, like, I could not figure out the difference between, like, there, and there till, like, I was in, like, 6th grade, 7th grade. I was, like, refused to learn it for some reason. Funny stuff. Look at us now, failing at programming, so. Alright, let's keep chugging. If you guys are new, like, let me know more about yourselves as well. Like, I have like I'd say, I have a degree in human biology and minor in chemistry, and I work as a formulation chemist. And let me know if you guys are in college, SCS majors. I honestly am pretty jealous. If I could go back and do college over again, I would really go back and do computer science. I think I could get a lot out of it. I'd be literally like best friends with my professor and my TAs, and just be all up in their ear and asking them everything, learn as much as I could. Like, I don't know, I just feel like I'd really try my best to take advantage of all the money I would be spending on it, and, like, really getting after it. But then again, when you're in it, you can be kind of demotivated too. So, all in hindsight, right? Let me know more about yourselves though. Where are you guys from and everything. Okay, let's go ahead and do number 6. European countries use a 13-digit code known as a European Article Number, or EAN, instead of a 12-digit Universal Product Code found in North America. Each European Article Number, or EAN, ends with a check digit just as a UPC does. The technique for calculating the check digit is also similar. You add these together, and then you multiply by the first 3 and add the second sum. Multiply the first sum by 3 and add it to the second sum. Subtract 1 from the total. Compute the remainder when adjusted the totals, and subtract 9 from the remainder. Okay, so now your job is to modify this to compute a EAN. The user will enter 12 digits. Okay, so let's go back to this guy and copy it over. And then what we're gonna do is we have 12 digits now. So this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we need a so what is 11th digits? What about the 12th digit? Add the 2nd, 4th, 6th, and 12th digits. Okay, so should I just do let me just do let me just do n, I guess. I'll throw on an n for like this, and I'll take this and copy it down, do an n here, and then do that. And then what we'll do is we compute the first sum, which is the second, the fourth, the sixth. I don't like this. It's kind of annoying. It's kind of making, I don't like having to think about all these different things. Okay, so this is first, second, third, fourth, fifth, sixth. So think of it just 0 index. Yeah, that's fine. Okay, so then we'll do the second, fourth, sixth, second, fourth, sixth. So this is I5. Oh my god, I'm not gonna do this, dude. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. Funny. Okay, I'm done with that. So then we're gonna go 12th, 11th, 10th, 9th, 8th, 7th, 6th, 6th, 5th, 4th, 3rd, 2nd, 1st. Nice. Okay, so first sum is going to be 2nd plus 4th plus the 6th plus the 8th plus the 10th plus the 12th. And then our second sum is going to be the first third plus the 5th plus the 7th plus the 9th plus, oh, I spelled 9th wrong, I'm stupid. Ninth. Yeah, I said 11th. Hey, thank you so much, KLD. Oh yes, I know. I got you guys. You guys are funny. We're just following the structure of the book. We're just following the structure of the book. We've been teaching ourselves Python for like over like a year and a half now, and we definitely have built some projects and stuff. But the book just hasn't introduced loops yet, so it's pretty. We're stuck in this without loops right now. Hold on, I gotta plug in my phone. So we're trying to solve the problems of the book with what it's given us. And it hasn't given us loops or arrays yet, so we have to do it this way. Okay, so 11th digits. Multiply the first by 3 and add to the second sum, and then compute this check digit. which is just 1 minus the total from 1, 9 minus the module by 10. Okay. I think that's it. So we want to check this code now. Alright, this is the last programming project here of chapter 4, and then we move on to chapter 5, which is probably where we start learning loops and arrays, you guys. So this is finally we break the chains. We're free. Okay. Let's go ahead and compile this bad boy. No. We declared 9th and we forgot to change it. There we go. Alright, here we go. Oh, we need 12, right? Alright, let's restart. Gotta make it official. Alright, 12 digits. So we have 86914842600. No. Bro. Oh. 86914 8426 000. Oh. Okay, where's our typo? 12th, 11th, 10th, 9th, 8th, 7th, 6th, 5th, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. Oh, no, we want to keep it by 10. So we want to take one digit off. We're not trying to convert it. Second, maybe we have something wrong here. 2nd, 4th, 6th, 8th, 10th, 12th. 2nd, 4th, 6th, 8th, 10th, 12th. 1st, 3rd, 5th, 7th, 9th, 11th. Multiply the first sum by 3 and add it to the second sum. Subtract 1 from the total and compute the remainder when divided by 10, and then subtract that remainder from 9. Okay, let's see if we will. Let's go printf. Let's do a little debugger. Let's throw in here this guy, first sum. And then let's go ahead and throw in this here. And then we'll do second sum here. Let's go and throw it in here as well. And let's print out the total. We're going to really give this a run for its money. Eight 86914842600. 23. Okay, we're trolling. Well, what is going on? 23 for our first sum. That's off. No way. 9 for our second sum. That's way off. Okay. Oh, they use a 13-digit code instead of a 12-digit code. Yeah, so they enter their first 12 digits. First, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 12th. um, 86914842600. 8. What? Might be past my bedtime, you guys. Zero. Zero. I wonder, is it because this number is too large? Is that too large? Or is it just me? Well, you can't do that. Never mind. This is a big number. Right, what if this is just too large? Use long. Okay, let's try that. Oh. So a long int. Okay. 86914842600. Oh, let's go. Yes, we figured it out. Okay, cool. Nice. I'm glad that we were able to recognize that. That the number was too big. Like, nothing was wrong with our math, but we were getting a garbage value for all of our summations because the number that it was actually reading from our memory location was wrong because we had the wrong type declared for it, right? Because it was too many bytes in for this integer. Or bits, or whatever. Let's go. Let's go. Awesome. int64_t, is that like a different type of declaration? Yeah, we're definitely not, we haven't gotten to all those ones yet. I have no idea what you're using C to do, but that's a W. Thank you so much. Appreciate you. No, we're just doing some practice problems, getting some familiarity with C, trying to use it to kind of propel our, current Python data science learning even further with maybe even be able to like write, faster programs in C and port those in, and even just better computer science knowledge is, I want to just become a better computer scientist as well as physical scientist, and use the two in tandem, and see what we can do. I don't know. Nice. So we had to use long on the number there, and it was really nice because I was like, man, like I like used some print statements to debug, and it was still wasn't getting us the right numbers. So I was like, well, usually when we're getting wrong numbers or like garbage numbers, something's going on with like memory. So it's like I went up here to our declarations, and I was like, okay, we're int for the number, but this is very, very large. And so it just kind of popped in my head, remember from our reading, that we need to declare. Now I tried, what was it? What did I try before? I literally forgot. What did I try before? What did I try before? What did I try before? I tried... Why can't I think of it? I literally just like lost it. Not long. Not int. It was... What did I try before? Double. Double, that's right. Double. Thank you so much, Blake. And I got mad. That's right. I just wanted to remember that. Double. That's exactly it. Because int is different in 16-bit architecture, like 2-byte, and in 64, it's 4-byte. And because int is different in 16-bit architecture, it's 2-byte, and in 64-bit architecture, it's 4 bytes. If we use int 64, it will only give 64-bit in every architecture, I think so. Okay, so you can specify even further than long by declaring int 64. Is this in some sort of package, or how do you do that? We haven't learned about it yet though, but int. How do you declare that specifically? 64t? Oh, underscore t. Also, you can allow you to control and direct parse the binary for int 16 underscore t, int 8 underscore t, etc. Okay, so if we want, we can explicitly set the size of a variable, like with this for like compiler's sake or whatever, even further. Now this is no different. Now tell me this. What's the difference here between doing this? We haven't gotten to this in the book, but I've obviously seen some videos and stuff. What's the difference between doing this with a variable and declaring, right, declaring an array of X bytes, right? Like how does that differ, if anything? Because that's what's really interesting to me is the whole memory aspect of programming. That's what's really drawing me to this. Is a lot of people kind of are fearing away from it, but I kind of like I'm really, really interested to know, like, how are these numbers being interpreted into what I'm writing? And I want to be able to, like, I really want to know. Like, it's super. I'm really curious. But yeah, that's. As a newbie, you should not get too deep like that. Learn the superficial stuff first, think it more on the level, and explore everything, then repeat. Yeah, exactly. That's why we're going through the book. We're only in chapter 4 here, but we used long here because it was I think it did give us long here in the book as well as the. I think it gave us long in this chapter. Or maybe in one of the previous chapters. Let's go quickly. Let's just do a quick scan. No. I think it would be in chapter... Would it be in chapter 4? No, it might be chapter 2 then. Well, yeah, no duh. That's all that's left. There we go. One line long. No, a semicolon. Is it chapter 1? No way. No, we haven't even defined long yet. I'm gonna search 800 pages for the word long. No. Chapter 2 notes. Okay, yeah, so we got some types here. So int, short integer. So short integer. Okay, interesting. Let's go back to chapter 2 and see if it mentioned long anywhere in chapter 2. I'm curious because I want to know how it expected you to solve that problem without knowing to convert that variable to a long. If that 12th character is what cut it off, right? Identifiers. Float int. Because like in our problem 5 here, 11 characters worked under the int that they declared here. So let's go really quickly. Let's take a peek at back in chapter 4 here. Right, at the UPC code here, they declare int for, oh, well, they're declaring int, they're declaring all of the variables. And they're scanfing all of them in. Or they're just doing it one at a time here, and then these. We scanned them all in at once. And we saved it into a number variable, which is what it wanted, right? Or we could have done, what we could have done is we could have just done a bunch of %Ds with the one field specifier in there, and then just done 12 of those, and then put in our variables. That would have also worked. And then we wouldn't even need to do this. Let's get caught up here. Just binary at the end of the day, it just means certain function libraries are happy and person. Network code have packets, their 2-byte number followed by a 4-byte number, and you have to parse in that order and what that size is to tell them apart. Yeah, I saw some stuff like on like Toralize and stuff on some YouTube A little bit of a similar, but not heaps. Thanks for coming in, Tanko. I appreciate you for stopping by tonight. You're awesome. Have a great night. Appreciate everybody for being here and joining me. Okay, I'm gonna take this. I'm gonna put it here. I'm gonna say, I guess I could have just done the %1d and 12 times and listed my vars as the my vars instead of the math. Exactly. What you're doing repeatedly divided by 10 works, but it's a bit long-winded. You definitely could simplify this output to just do this with a bunch of %Ds in the scanf and then compute that. Why it's easier. So it's interesting because adding the 12th value going from UPC to NPC what was it? EAN made it have to become a long declared var. That's a subtle but important detail. Here's what's happening. A UPC has 12 digits total, 11 digits plus 1 check. The EAN is 13 code, which adds 1 more digit. The key is now too big. The key is how big those numbers can get. 12 digits, it can now reach up to this, which fits up to a 32-bit int on some systems, but it's right on the edge. A 13-digit number like this can go up to this, which exceeds the maximum value for a 32-bit int. That's why you had to switch to this, or even better, long, to safely store all 13 digits. Most systems use int equals to 32-bit, which equals to a plus or minus 2.1 billion. A long goes to 64 bits on modern 64-bit compilers, but 32 bits on older Windows compilers. Long guaranteed at least 64 bits. So for portable code that always works with 13-digit numbers, the safest is long. Oh, okay, so there are some quirks here. And then you need to receive a long digit or decimal number. So break down long. Both are extended integer types. In C, you have several standard integer types with increasing range. An int takes into up to 32 bits on typical 32-bit systems. So this would be int 32 bits with a max value of about 2.15 billion with it takes in these printf, scanf formats. A long 64-bit on Linux and Mac OS or 32-bit on Windows. Okay, so long has some variability on operating systems. Takes in up to crap ton more numbers and has these values: long digit or decimal and long integer. A long forces 64 bits across all operating systems for this value, okay, which is, how big is that? That's a million, it's a billion, trillion, is that a quadrillion? Was that a centrillion, or what is that? How big is a long? A long is at least 64 bits. That's the minimum guaranteed by the C standard, C99 and later. Let's unpack what it means. A long, 64 bits or 8 bytes. So 8 sets of 8 numbers, right? Or sorry, Yeah, 8 times 8, 64 numbers. No. 64 bits, or 8 bytes. This is not 64 numbers. It's just 19 digits. Ranges 0 to this unsigned. That's about 18 quintillion. I was kind of right, quintillion. Or so no, I said centrillion, my bad. Plenty of room for things like UPCZ and timestamps in milliseconds. Wait, no, at 8. $64 bits or 8 bytes. So when you say 64 bits or 8 bytes for computer architecture, does that mean that the highest number the computer memory can process is 64 bits long, or 64 ones or zeros? And is that like a, I'm trying to figure out, I've never really understood it, like a single row where there are many rows. Like, that's exactly the kind of deep thinking of this clip. Let's unpack this. 64 bits actually means. When we say a 64-bit system, what we're talking about is about the width of the CPU's registers, the chunks of memory inside the processor that it uses to perform calculations and address memory. So the CPU can handle 64 bits or 8 bytes of data in one instruction. That's 64 binary digits, either 0 or 1. So the CPU can handle either 64 bits of data in one instruction. Each register is basically a row of 64 little switches or bits. Example, boom, right? That's one 64-bit binary number representing the value of 1. Now memory layout rows. Think of RAM main memory as huge grids of bytes, millions, actually billions of tiny bit cells, each with their own address. Each byte, 8 bits, right? Each bit is 0 or 1. When your CPU reads from memory, it fetches some number of bytes at a time. On a 64-bit CPU, it can read 8 bytes, 64 bits in one go, like grabbing one full row of 64-bit switches in memory. So yes, you can imagine memory like rows of 64 bits each, but that's a simplification reality. The hardware is wired so that it can access 64 bits efficiently. It doesn't mean memory itself is literally divided into 64-bit rows, just like 64 bits is a native chunk size for operations. There are two key uses of 64-bit. Register width. The CPU can process 64 bits of data in one instruction. And then address width. Memory addresses themselves are 64 bits wide, meaning the CPU can theoretically address 2 to the power of 64 bytes of memory. So whoa. Address width. Memory addresses themselves are 64 bits wide, meaning the CPU can theoretically address 2 to the power of 64 bytes of memory, which is about 16 exabytes. So a 64-bit system can point to or manipulate memory addresses that large, though your computer obviously doesn't have 16 exabytes of RAM. How this connects, so this is a little confusing to me. When you declare long x, you're telling the compiler, store this integer in 8 bytes, 64 bits of memory. So we're reserving in our memory 64 strung out zeros or ones, right? for this variable. And we are making sure that on whatever operating system with this long declaration that we are getting 64 zeros or ones in whatever combination to make up the value of this number. This means the binary representation of x might look like this. Perfect. Each bit doubles the possible range. Each bit doubles the possible range. Oh yeah, okay, cool. So one bit can either go 0, 1. We add this, that can become 2 bits now. We add another bit, that can become 4. We add another bit, that can be 8. That can be 16. Right, so on and so forth, so forth. 32, 16. So each bit doubles the range. 8 bits is 256 combinations. 16, boom, boom, and 64 bits gets us the 18 quintillion. Analogy, thinking visually. Imagine each bit as a light switch, on or off. A 64-bit value is like a row of 64-bit switches. Each unique pattern of switches corresponds to a number. More switches equals more possible combinations, which equals to larger numbers. Yeah? Memory, on the other hand, is like billions of these rows stored one after another, each row being 8 bits or 1 byte. Summary. Oh, okay, right. So, right. That's why you have those addresses in bytes, and then you can gather a bunch of bytes together. So is that what's going on like under the hood, like in the assembly code? Is that like this long is reserving 64 bits, which is 8 bytes, and those 8 bytes in memory can be kind of anywhere. Do they have to be like within sequence in each other, like? Unlike like a char star or something? Like, can we get the first chunk, second chunk, third chunk of a number and really bring them all into the right area? Whereas with like a string, a char star, it's like a sequential until you hit the delimiting character or the escapes character in memory, right? So bit once, yeah, got you. So my next question is then, so when we talk about memory addresses or places, like you said that they are, you said that memory address, each row is being 8 bits or 1 byte, and there's billions of these rows stored together. So when we call like longs and reserve 64 bits or 8 bytes of memory for this integer value, are those 8 bytes randomly sequenced, or are they in a specific sequence in or like char star or whatever, where you have the string of characters in line with one another until you hit the escape character or delimiter. This song sucks. I couldn't even think. It was distracting me so bad. I like lost my train of thought. And this one's not much better. We gotta switch it up. Did that not really take my word? Come on, dude. So you said that the sorry, I'm not reading chat, you guys. I'm just on like a train roll right now with my thoughts going out right now. I'm trying to just get it all out there. So you said that the memory rows are 8 bits long. Are these ints or longs that are made that have multiple bytes in a sequence, or are they random in memory with just pointers to them and order on the back end? Unlike a char star, where the characters are in order until you hit the limit, right? Now we're getting into the difference between raw memory layout and how C abstract types. Memory is just a big grid of bytes. At the lowest level, RAM doesn't know about int, long, or char. It's just bytes, each 8 bits with a unique address. When you declare, each 8 bits has a unique address. When you declare a variable with C, in C, like this, the compiler decides where in memory to store it. Say I address this, and how many bytes it needs, typically 4 bytes for an integer. Those 4 bytes are consecutive in memory. Okay, so even with the integers, the CPU accesses all 4 bytes at once and tells it this is an int, so read 4 bytes together. So a memory row of 8 bits isn't inherently an int or a long, it's just the smallest addressable unit. Types are logical groupings of bytes that the compiler and CPU treat as one unit. Multi-byte types. When you declare a multi-byte type, char, which is 1 byte, 1 consecutive byte, int, 4 bytes, 4 consecutive bytes, or long, 8 bytes, or 8 consecutive bytes, the compiler lays these consecutively in memory. The CPU reads/writes them into chunks corresponding to the type. The order of bytes in memory depends on endianness. Little endian, or x86, which is the least significant byte first, or big endian, most significant byte first. For example, long, which is at this, which x is equals to this. Okay, so in little endian memory, address x10000 has a value of 8. 8, 7, 6, 5, 4, 3, 2, 1 for the values at those addresses. And then in big endian order would be in the opposite direction. A single variable like int x or long y has one memory address, which points to the start of its bytes. And an array of int or long is consecutive in memory like this. Int array of 3 has these 3 values. Array index of 0, 4 bytes at the start. Array of 0 has 4 bytes at the start. Array of 1 has the next 4 bytes. Array 2 has the next 4 bytes. Yes, or indexing. The compiler ensures this order in memory. You can even do pointer arithmetic. Okay, we don't need to get in that yet. Let's go a little crazier. So the consecutive memory blocks. So then, can you explain this? This is a really important concept to confuse address with data width. What is memory address? Every byte or sequence of 8 bits in our computer's RAM has a unique number called its address. Simple enough. Think of RAM like a huge row of mailboxes, each holding 1 byte. The address is just a number of the mailbox. A CPU needs to know which mailbox to read from or write to. Address width. When we say a CPU has a 64-bit address width, it means that the CPU uses 64 bits to identify a memory location. How many unique memory locations can 64 bits represent? Each bit can either be 0 or 1, so 2 to the power of 64 unique addresses. Each address points to 1 byte, so the CPU can technically read to this many memory addresses, but we don't have this much RAM. Okay, got you. Or memory. That's why 64-bit architecture lets the CPU use enormous amounts of memory. And that's why they say that we won't typically run out of this much memory for a while. Or we won't exceed this for some time, right? Until some time in the future. I'm not sure when. much more than 32-bit CPUs, which are limited to only 4 gigabytes. So just by that power increase, right, that exponential increase drastically changes the, that was like a huge shift, I bet you, in like time. If you were like a computer scientist back then, going to these different architectures when it became standard. Got a lot of chats here. People seem to be liking the program. Let me get caught up here. I'm interested in risk V, which is what's your take on that risk V? Okay. Bye for now. Low on battery. Wish luck. Thanks so much for coming in, dude. 64 bits is 8 bytes, assuming you're working on modern hardware. Some funky old systems like 1980s, etc., could work on 6 bytes. 6-bit bytes. Oh wow. Gets even funkier if you look into CPU register mapping and instruction registers, etc. Registers are 64-bit rows, while wider DRAM isn't. DRAM isn't. Yeah, it'll be reserving 64 bits at a location of address X. The compiler handles organizing the binary data in the final executable. That's why C is still considered high level by some. Yeah, there's still some final like interpretation going on, right? Based on those types. You're not actually like you're not like specifying like which memory address or whatever, right? It's kind of has some interpretation going on as well. Real ones just make everything with transistors from scratch. Yeah, me in my garage, right? Hey Chris, thanks for coming in. Modern computers don't have 16 exabits of RAM. Far less, usually gigabytes or terabytes. But the CPU address could address that much memory if it existed. Even if it could address that much mem, would it even be efficient in today's hardware? That's a subtle but important point. Just because a CPU can theoretically address 2 to the power of 64 bytes doesn't mean it could be practical or efficient in real-world hardware. Modern computers have gigabytes or terabytes of RAM. Even the largest supercomputer doesn't come close to 16 exabits. The computer's ability to address this is mostly future-proofing. Even if somehow it had terabytes of memory, latency matters. Accessing RAM is slow compared to the CPU. Registers, 1 cycle. Level 1 cache, main RAM, disk SSDs, millions of cycles. CPUs uses caches and memory hierarchies to keep frequent use data use close. Okay, so your CPU caches like frequently used data. I thought that's what RAM did, but modern memory, so diff between CPU cache data and RAM. Think of computer memory like a pyramid. The closer to the CPU, the faster and the smaller it is. The further away, the slower and the larger it is. Okay, right? So if your CPU has a 64-bit architecture and can store up to a 64-bit number within one memory address, how can hardware like on the bottom of the pyramid hold more if you're bound by that architecture? Registers, tens of bytes, 1 CPU cycle. Level 1 cache, which is small. Oh, tens of bytes. So, tens of bytes, really small. Kilobytes. Megabits. Terabytes. Gigabytes to terabytes. 1 CPU cycle inside CPU, on CPU, on CPU, on CPU, off CPU, on the motherboard, off CPU. Why cache exists. CPU runs extremely fast, gigahertz speed, executing billions of instructions per second. RAM is comparatively slow. Even fast DDR5 takes about 100 nanoseconds, which is hundreds of CPU cycles. If the CPU had to wait for RAM for every instruction, it would stall constantly. Stores copies of frequently used data and instructions closer to the CPU. CPU first checks level 1, 2, 3, and then RAM. The first place it finds the data is called a cache hit. How data moves. CPU wants data from an address in RAM. Level 1 cache, check, hit, use immediately. Miss, check level 2. Go so on and so forth. Just like a queue of checks. The data is copied into cache so the next check is accessed faster. If the architecture is 64-bit, how can the computer 64-bit, meaning that the CPU can read memory. Is it read? Is it write? Memory. That is 64 bits or 8 bytes long. How can it read the larger data at the bottom of the pyramid? Now you're asking some really important questions here. How do CPUs handle large data that exceeds their native width? So a 64-bit CPU has 64-bit registers and is 64-bit registers not a memory limit. A 64-bit CPU can natively process 64 bits or 8 bytes at a time in its registers. But that doesn't mean that it can't handle larger data in memory. Arrays of integers, long, structs, images, etc. The key is that large data is split into chunks that fit into the CPU's registers or cache lines. Accessing larger data in memory. CPU can read data in chunks. The CPU doesn't have to load the entire data at once. It loads memory into units called cache lines, typically 64 bytes on modern CPUs. Example, a 52-bit vector, 64 bytes. A CPU requests the memory location. Memory subsystem copies 64-byte cache line containing that address into cache, level 1. So this is 64 bytes, so this is quite larger than 64 bits, or 8 bytes, right? So this is 52 bits. So we need to request, so copy 64-bit cache line into the address into level 1 cache. CPU processes the data into multiple 64-bit chunks sequentially or in parallel with SIMD instructions. Even though registers are 64 bits, the CPU can handle bigger objects by processing them piece by piece. For larger integers like dunder, int 128 in some C compilers, or big floating point numbers, CPU performs multiple read/write cycles. Each cycle moves 64 bits between memory and registers. So an example where we have a 128 big variable and some large value is assigned to it. CPU might load the lower 64 bits first, then the upper 64 bits, and compare them internally. And combine them internally. Role of caches. CPU caches help bridge the speed gap. Yeah, we talked about that. The warehouse, RAM, has huge boxes of supplies. The worker can only carry 8 bits at a time. To process 8 64-byte box, the worker picks up the first 8 bytes, works on them, then does the 8, then repeats until the work is done. The cache is like a nearby mini storage area where the frequent access boxes are already partially broken down into 8-byte trays. Let's get caught up on chat here. Probably got a lot of questions or people chiming in here. Though you can specify addresses if you want, I believe. Or did you get that C programming document? This is C Programming: A Modern Approach by K.N. King, 2nd edition. It's got a lot of great. We're on chapter 4. We just finished the chapter 4 programming exercises at the end, so we are ready to move on to chapter 5 called selection statements here. But we're just getting some. I honestly have had these questions on my mind for a long time because I've been really kind of struggling with, bits, bytes, binary memory, all that kind of stuff, and really actually bring it all together. So this is really cool that we were able to get some more info here. I really needed that, actually. Cool. Anyone know if x86 SAMD? I can't remember. I often hear that thrown out there when you say x86. What exactly does that mean? I got something in my eye. Also known as x86, Intel AMD is the designer. Also known as 80 by 86, or the 8086 family, is a family of complex instruction set computer. Instruction set architecture developed by Intel based on the 8086 microprocessor and its 8-bit external bus variant, the 8088. The 8086 was introduced in 1978 as a fully 16-bit extension of 8-bit Intel's 8080 microprocessor. The memory segmentation as a solution of addressing more memory than can be covered by applying 16-bit address or 2-byte address. The term x86 came into being because the name of several successors to Intel's 8086 processor ended in 86, including all these other. Okay, got you. So they're just kind of like a line of processors, modern day processors that has 8-bit external bus variant. No, that's the 8080. As a fully 16-bit extension of the 8080. The term is not synonymous with IBM PC compatibility. In 1980s and early 1990s, when 8088 and 8286 were still in common use, the term x86 usually represented an 8086 compatible CPU. Today, however, x86 usually implies binary compatibility with 32-bit instruction set of 80386. This is due to the fact that the instruction set has become something of the lowest common denominator for many modern operating systems, and also probably because the term became common after the introduction of the 80386 in 1985. A few years after the introduction of the 8086 and 8088, Intel added some complexity to its naming scheme and terminology as the IAPX of the ambitious but ill-fated Intel IPAX 432 processor was tried on the more successful 8086 family of chips, applied as a kind of system-level prefix. It's really interesting, how detrimental Intel has been for developing being a grandfather of modern. I mean, they still are, obviously, right? But just this year in 2025, people were retail investors were calling for Intel to go bankrupt, when it seems like if that were to happen, bad things would really happen, and I don't think people would let that happen. What do you guys think about that, for the computer scientists that know more about this, that are in here? What do you think about what would happen to Intel if it actually went belly under as a company? Let's ask. Earlier this year, many people thought Intel would maybe go under. I am learning about its basically detrimental. Oh my gosh, so bad. About its grandfather like hold on the computing industry. Theoretically, what would happen, or is it even possible for Intel to go under? Would the world even allow it to happen? We're just like conspiracy theorying now. It's like 3 a.m. So we got to start working out the conspiracies. Yes, Intel, the grandfather of modern computing chips, practically a household name in CPUs. Technically, yes, right? Any company can go under. If Intel had catastrophic revenue losses or that couldn't recover, AMD or others could make Intel irrelevant. Could lag far too far, right? But, and this is huge, Intel's way too big and integrated into global economy for this to happen quietly. Would the world allow it? Not really in a literal sense. Intel is a crucial infrastructure. See PCs and servers, tons of data centers, enterprise systems, right? Semiconductors, supply chains, national security. If Intel were in serious trouble, you'd see bail. So I think that's why we got that bailout this year, dude. Is that why Intel got that huge USA government contract bailout this year when facing pressure? Exactly, a big part of it. The government has been increasingly worried about domestic semiconductor production. It goes deep, you guys. Would potentially open up to many competing CPU standards, which would be good and bad, though it already is happening to some extent with ARM CPUs and mobile phones, and even Apple Silicon's different. But like think about like all like the servers and like all those old, like I think it's like crazy, like, right? Like it's really interesting to think about. Stepped into support through contracts and subsidies. Yeah, dude, I bought them up at 19. My dad still has his shares, but I sold mine at AMD exists. They were the first to introduce the x86-64. So even if Intel goes down, AMD will be able to satisfy some of the demand for the x86-64 CPUs. Also, a lot of modern laptops still getting ARM. When you guys have said this quite a bit, I'm sorry, I just don't really know. What is ARM? When you say ARM, I hear this a lot too. Intel going under would be wild. Intel is a behemoth of electrical computer engineering and silicon development. Yeah, that's what I was like really curious about, because there's a lot of like, whispers and like really like fear over Intel's future over this past like 2 years, and learning more and more about these processors and memory and how much I keep running into Intel and all these companies, these roots in these companies, and to hear about one of them struggling so bad, it's kind of interesting to see what would happen to like all the support for their hardware that's still being used, that's kind of dated and whatnot. I know ARM is a British CPU company, and so from the stocks, but is that what you're referring to? ARM is a different CPU architecture? Oh, it's just a different architecture? Like another name for one? So x86, that was just a line of processors that were able to utilize general purpose 16-bit, 8-bit, 8 GPRs, including BP and SP, 32-bit GPRs. Okay, so there's x86. Oh, and then they introduced different models on top of x86, such as x86 32 and x86 64. So in 1985, the 32-bit x86 variant came out. And then in 2003, the 64-bit x86 variant came out. So let's go here. x86 64. Man, something is in my eye, y'all. An x86 64 processor acts identically to an IA32 processor when running in real mode or protected mode, which are not supported modes when the processor is not in long mode. Is this about long mode? No, I don't really want long mode. I want x86 64. x86 64, also known as x64, 8664, AMD 64, and Intel 64, is a 16-bit extension of the x86 instruction set. It was announced in 1999 and first available on the AMD Opteron in family in 2003. Man, dude, like, I just feel so stupid for like not seeing like the writing so clear on the wall for like these early investments. Like, yeah, I was young, right? But like, only if I would have known, dude. Like, it just seems so clear. Like, AMD, like their stocks were like at nothing, and they're like building all of these things that were used in these infrastructures to come, and like it's just like such a blatant, like, no-brainer $1 million play. So crazy. Just like so loud right in front of your face. It was announced in 1999 and first available in AMD Opteron family in 2003. It introduces two new operating modes, 64-bit mode and compatibility mode, along with a new 4-level paging mechanism. In 64-bit mode, the x86 64 supports significantly larger amounts of virtual memory and physical memory compared to 32-bit predecessors, allowing programs to utilize more memory for data storage. The architecture expands the number of general-purpose registers to 8 to 16 at a fully general-purpose. All fully general-purpose and extends their widths to 64 bits. Cool. I'm finally starting to understand what this stuff actually means. Now I've got a long way to go, but that design CPUs, etc., and open source them. Notably, they don't have an x86 license, so they don't use that architecture. Historically, did a lot of embedded design, but in recent times is branching into more mainstream offerings. x86 is a chipset that's popular and became the standard for instruction set in terms of assembly since like the 80s. Interesting. Why did they have to come up with like the hardest names ever? It's honestly like BMW and coming in their car names. Like, can never figure those out. I wish they. I mean, it can't be any worse than Apple Pro Max, Apple Pro Maximum Maxer, Apple Maximum Max Pro Max. Can't be any worse than that, actually. So at least they have distinguished names. CS is like an endless void. It's so cool though. It's like, I don't know. It's really fascinating. Thank you so much, Tucson Bear, for the follow. Appreciate you so much joining me here on Twitch. I guess that's why everyone says to pick a niche. Well, should we, building, next thing you see on my channel, building microprocessor from scratch in my garage. Building custom foundry in my garage, microprocessor, x86, attempt, V1. That's funny. Alright, you guys. Just go and work in Power, then knowing Python, do graphs, and impressive for coding. Alright, you guys. I think I'm going to head out for tonight. If you guys could leave a like, it's completely free to do so. for this late night stream. It's 2:50 a.m. for me. I don't really do these kind of late nights that often, so if you enjoyed it, please leave a like. We were able to finish up today the all of chapter 4. So earlier in the earlier stream this evening, we did the exercises, and then we just completed the programming projects for chapter 4. So let's go ahead and add these up. If you guys want to get access to this book, I have a copy and link stuff in my Discord completely for free, all in there. Kind of like a roadmap of all my learning. My GitHub is in the description below. Finished chapter 4 programming projects. Chapter 4 complete. Nice. Feels good. Alright, you guys have a great night. Thanks so much for being here, everybody. I'm gonna go hop in, cuddle the dog. I'll see you guys later. Bye, guys. Have a good evening. I'll see you in a couple hours. Peace out, y'all. Be back tomorrow.